line. Calculate the wavelength of the spectral line produced at the hydrogen spectrum when an electron falls from the 10th Bohr orbital to the 4th. Report your answer using 3 significant figures. Alright, so we're looking for that equation. Let's see what page it's on. Page 318. You can see the equation there. Whoops. Page 318. Let me get my calculator. Where is my calculator? Calculator. Oh, yeah. All right, so page 318 there, we see that we can identify the, what are they asking for, 389? Calculate the wavelength. We can use that equation about the middle page of 318. We can calculate the wavelength using the equation given there, where we have the low and the high. And the low is going to be the 6, right? The low wavelength or energy level from the 10th to the 4th. So the, sorry, not the 6th. The low is the 4th. So we have 1 over 4 squared. That's the low. Minus 1 over 10 squared. All right, and all of this is multiplied by b, which is a constant, h, a constant, and the speed of light, which is a constant. All right, and let's verify here. It says down there BHC has a value of 109,730 per centimeter. So this is 109,730, and that's per centimeters, right? So, and this will give us a per wavelength there. Yeah, that's okay, right? Well, let's see, what's C equal to here? Oh, no, that's all combined. This is all combined. Oh, no, sorry. Messed this up. So this is our B over HC, right? 109,730. So 109,730, and that's centimeters to the minus 1, or per centimeters. Okay. So now if we use this equation, this will give us our wavelength, but it'll be in centimeters. So 1 over 4 squared, 1 over 16 minus 1 over 100, 1 over 10 squared. All right, so 1 over 16 minus 1 over 100. All right, so this is equal to 0.0525, right? Times that by 109,730, and that equals, this equals 5,760. And we take 1 over the wavelength, is 5,760. So if we take 5,760, oops, and then take the reciprocal of it, so I'm getting 1.7 times 10 to the minus 4th centimeters, all right? And if we want to convert that to, well, I don't know, what did it say, what units we wanted in? 889, and the visible region, let's see, falls from the 10th, which region of the electromagnetic spectrum, UV, vis, or infrared, is the line. Okay, so we just have to see whether it's in the UV, the visible, or the infrared. 1.7 times 10 to the minus 4 is 0.00017 centimeters. And if we convert that to meters, or I guess we go the other way, convert that to micrometers, 1, 2, 3, that's 0.17 micrometers, or 1,000, or 1, 2, 3, go to nanometers now, 170 nanometers, right? So this is going, oh, no, sorry. Start that over. Centimeters, this isn't meters, this is centimeters. So if we want to go to meters, excuse me. If we wanted to go to meters, we would go 2 the other way. And then if we wanted to go to millimeters, we would go back 3. So that's 0.0017 millimeters. or 1.7 micrometers, or 1,700 nanometers. So 1,700 nanometers, that's in the IR range. All right, so let's take a look at that. 889. 1,700 times 10 to the minus 6. 1.7 times 10 to the minus 6. We were not expecting to see this light. It is not in the visible range. Let's see, is that right? 1.7 times 10 to the minus 6. Yeah, 1.7 micrometers, yeah. All right. Okay, 889, 891. What is the letter code for the subshell with L equals 1 and L equals 3? All right, so L equals 1, L equals 3. The letter code, when they refer to the letter codes, what we're talking about is our S, P, D, and F. All right, S, P, D, and F, they stand for sharp, what is P? I can't remember what P is. Diffuse, fundamental. But you don't have to remember that, and that's not what they're for. The point of these letter codes is these were the orbitals, the orbital shapes, right? An s orbital is spherical. A p orbital is dumbbell shaped, like this. D orbitals are also dumbbell shaped, but there's 4 lobes on them. An f orbital is also dumbbell shaped, but there's 6 lobes on them, right? So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. There. So these aren't SPDF are these different orbitals that there are, and we don't even really have to remember that too much. We should remember the S and the P, and we can also kind of keep in the back of our mind the fact that D has more lobes than the P. But the important thing is to remember that these SPDFs correspond to quantum numbers. The L quantum number. And the L quantum numbers that they correspond to is 0, 1, 2, and 3. So L equals 1, that's the p orbital. L equals 3, that's the d orbital. Oh, let's see here. All right, so L equals 1 is our p. L equals 3. Not our D or F, sorry about that. L equals 3 is our F orbital. Okay? 893. What are the values of N and L for the following subshell? Okay. N and L for the following subshell. 3S. 3S. Well, the N value is always represented by this first value. So N here equals 3. And when N equals 3, L has a choice. L can either be one of 3 different numbers, starting at 0, 1, and 2. All right? So N, if N equals 3, L can be 0, 1, or 2. And in this case, 3S, so N equals 3 for that value, and S is our 0. So the N equals 3, and S, or L, equals 0 for those values. For the D, or for 5D, N equals 5 and D equals 2, or L equals 2 for D. All right, so we can double check that one, 891 in the back. Wait, no, 890, that was 893, right? 893. And 3, L0, and 5, L2. Okay, 893, 895. For the shell with N equals 6, what are the possible L values? Well, if N equals 6, L always equals N minus 1 down to 0. All right? So N minus 1 down to 0. So if N equals 6, L can be 5, 4, 3, 2, 1, or 0. And there's always the same number of possible L values as N values. So if N equals 6, there must be 6 of these, but it goes down to 0. So it starts from 0, 1, 2, 3, 4, 5. Okay? So 897, what are the possible values of M sub L for a subshell with L equals 1 and L equals 3? 897. If L equals 1 and L equals 3, what are the possible M sub L's? M sub L. Well, M sub L can always be plus L all the way down to minus L. So in this case it's 1, so it can be plus whatever L is, and then we go down until we get to minus L. We go down in integers until we get to minus L. And so M sub L's possible for L equals 1 are plus 1, 0, and minus 1. M sub L's possible for L equals 3 are going to be plus whatever the L value is, that's 3, all the way down to minus 3. So we have a plus 3, a plus 2, a plus 1, 0, minus 1, minus 2, and then the minus 3. All right? So M sub L is always plus to minus L value. All right? That's 897. 899. If the value of M sub L for an electron in an atom is minus 4, so M sub L is minus 4, what is the smallest value of L that the electron could have? What is the smallest value of N that the electron could have? So if M sub L equals 4, that means L could, the smallest value it could be is 4, right? Because 4 would encompass minus 4 to plus 4. 3 would encompass minus 3 to plus 3, and that wouldn't include the minus 4. So L would have to be 4. And then the smallest value that N could be in this case would have to be 5, right? Because if N equals 5, then L could equal from 0 up to 4, and that would be the smallest value that N could be. All right, 899. M sub L is minus 4, 4, and N equals 5, so that's correct. All right, 8101. Give the complete set of quantum numbers for all the electrons that could populate a 2p subshell of an atom. 2p. All right, so give the complete set of quantum numbers for all the electrons that could populate the 2p subshell of an atom. So we want to find all the quantum numbers, all right? Well, if this is 2, that means N equals 2, all right? And if this is P, that tells us that L equals 1, right? These are the L equals those values for our different orbitals, okay? So if N equals 2, L equals 1, that means M sub L could equal minus 1, 0, or plus 1. And then M sub S could equal plus minus 1/2 for each of these. Plus minus 1/2 for each of these. Okay, so that should be the answer. So we can look here. So we have a scenario back there where N equals 2, so N has to equal 2 always, L always has to equal 1. Then we have the one with the minus 1 and the plus and the minus 1/2. One with the 0 with the plus or minus 1/2, and then one with the positive 1 with the plus or minus 1/2. All right, 8103. In an antimony atom, how many electrons? Let's change this up here. How many electrons in an antimony atom have L equals 1? How many electrons have L equals 2? And L equals 2. So we want to see how many electrons have L equal 1 and L equals 2. So we can use our periodic table, find antimony first of all. It's element 51, all right? So we have N equals 5, right? So if we write the electron configuration for antimony, if we try to write out all the electrons there, then that might help us a little bit, right? We have, starting with hydrogen and helium, those are our 1s2 electrons. And then next we have our 2s2, that is lithium and beryllium. Then we go into the 2p6, that is boron to neon. Then we go into our third row, 3s2. All right, that is potassium and calcium. No, sodium and magnesium, sorry. And then we go to 3p6, that is aluminum to argon. And then we go to our 4s2, that is potassium and calcium. 4 again is the fourth row. And then we have 3d10. And after 3d10, we have back to 4p6. That is gallium to krypton. 4p6 gallium to krypton. And then we have 5s2. And then we have 4d10 and 5p, and then we have 1, 2, 3, 5p3. 1, 2, 3, 4, 5, 5p3. Okay, so this is the electron configuration for antimony. All right? And now we want to look for all the electrons that have L equals 1. And when L equals 1, that's p. So there's the 2 p's, and that's 6 of those. 3 p's, that's 6 of those there. And we have this one and this one. So we should have 6 times 1, 2, 3. 6 times 3 is 18, 19, 20, 21. When L equals 2, that's D, 10, 20. So we should have 21 electrons with L equals 1 and 20 electrons with L equals 2. This is 103, 21, and 20. Good. L equals 8105. Given the electron configuration for these elements. Okay? Electron configuration for sulfur, potassium, titanium, and tin. All right, sulfur, potassium, titanium, and tin. Okay? Give the electron configuration. So for sulfur, we're going to have 1s2, 2s2, 2p6, 3s2, 3p4. Right? So we look at our periodic table. Let me just get a periodic table here so I can hold it up to the camera. All right, so for sulfur here, what we're doing, is that focused? We're looking at our 1s2, these two here, 2s2. We're trying to get down to sulfur right here. This is the 1, s2, 2, s2, 2p6, 3, s2, 3p, 1, 2, 3, 4. Okay? So 1s2, 2s2, 2p6, 3s2, and then 3p4. For potassium, we have all this stuff before. 1s2, 2s2, 2p6, 3s2, but then we have also 3p6. So we have all this stuff that was before down here as well. 3p6, and then after 3p6 we have 4s1. That's the potassium. For titanium, we have everything that was above here. And we have 4s2 and then 3d2, right? All right. So, and for tin, we have all of this 4s2, starting from 4s2, we go 3d10, 4p6, that is gallium to krypton, and then 5s2, and then we're going to tin, so we have 4d10, yttrium to cadmium there, and then we have 5p2, which is indium to tin. All right, those are the electron configurations for those elements. 109, how many unpaired electrons would be found in the ground state of magnesium, phosphorus, and vanadium? Or wait, 107. Which of the following atoms in their ground states are expected to be paramagnetic? Paramagnetic. All right, and paramagnetism means that the electrons are unpaired. Okay, so that there are unpaired electrons. So, and we can find that, where is that section? It's not a very big section that talks about paramagnetism. Page 328, Paramagnetism and Diamagnetism. For these atoms, the magnetic atoms with more electrons that spin in one direction than in the other, said to contain unpaired electrons. For these atoms, the magnetic effects do not cancel the atoms themselves because tiny magnets that can be attracted to the external electronic field. This weak attraction of a substance containing unpaired electrons is paramagnetism. Paramagnetism. And diamagnetisms are substances in which all electrons are paired and not attracted to a magnet are called diamagnetic. All right. So paramagnetic, again, means that there are electrons that are not paired. All right, and we'll try to show you what that means here in number 107. Okay. We're looking for which of the following in their ground states are expected to be paramagnetic. Well, we go to manganese, Mn first, manganese. We can look for manganese, and we can see that the last shell that's being filled is our 3D10. Our 3D10, or 3D shell. And the D shell is going to have 5, 1, 2, 3, 4, 5 M sub L values. These M sub L values, D is 2, it can be -2, -1, 0, 1, and 2. So these are the 5 M sub L values. And when we go filling this electron, we're going to be putting 1, 2, 3, 4, 5 electrons in because that's how many manganese has in this shell. We're going to be putting 1, 2, 3, 4, 5. And that's the rule, one of the rules. When we fill electrons, we have to fill them all with 1 before we pair up a second one. So this one is an example of paramagnetic. Which of the following atoms in their ground states are expected to be paramagnetic? That one's expected to be paramagnetic. Arsenic. In arsenic, we're filling, when we fill up the last shell, it's filling the 4p, and for p, the M sub L values are -1, 0, and 1. That's 3 orbitals, or 3 orbitals there. And each one of these is going to have, we only have 1 electron in each one because we're going from gallium to arsenic. So arsenic would be expected to be paramagnetic. Sulfur and strontium and argon. All right. So argon, well, so let's go through sulfur first. So this looks like it's paramagnetic because we have all these electrons are pointing the same direction and each one is half filled. Same thing here. Sulfur, you're filling the 2 or the 3p. Let's see, did we just do that incorrectly? The 2, 3, the 3p, 3p, and so we have 1, 2, here's our p orbitals, and sulfur, that's the 4 electrons filled. So we still have a degree of paramagnetism because there's 2 electrons that aren't filled. So sulfur would be expected to be paramagnetic. Strontium, the electron in strontium is going into the 5s. There's the s orbital. M sub L for s has to be just 0. So this is the only M sub L value that we can have. And we have 2 electrons. So we see that strontium is not going to be paramagnetic because it has no unpaired electrons. Both of those electrons are paired. Argon, and argon's a noble gas, and we can see that argon is filling the last electron in the 3p, therefore it is also not going to be paramagnetic. All right, so all of them are Manganese and arsenic are diamagnetic or paramagnetic. Sulfur is slightly paramagnetic, but it still could be considered paramagnetic. And strontium and argon are not paramagnetic. They're diamagnetic, right? 109. Page 109. How many unpaired electrons will be found in the ground state of magnesium? Well, we see magnesium is filling the 3s orbital, and there's one electron, one up and one down, so there's none there. No unpaired electrons in magnesium. Phosphorus, we see we're filling the 2p orbital, and we have 3 electrons there, so we have 3 unpaired orbitals. This is for magnesium. This is the 2p for phosphorus.